So hello everyone, I'm Wojtek. I'm working in Ukraine, as you can see, and I'm going to present you the presentation about isolation levels and read or write anomalies which can happen in databases. So first question to you, who is working or has worked with database? Any kind of? Yeah, that's the presentation for you guys. Rest of us who don't work with databases, probably you sometime will work with such kind of software, so it can be useful also for you. How will the presentation will look like? First, we will talk about the isolation. What is it? What is the definition in terms of database transactions? Then I will describe four read-write anomalies which can happen during reads or writes in databases and how to solve them. And then will be the time for questions. So I think that we can start. So let's go to the first topic, which is isolation. Let's say first about transaction. What the transaction actually is. The transaction is the set of reads or writes on the database which come in, well, one set. It can be described with ACID properties. Do you know, who knows the term, the ACID? Okay, that's good. Let's briefly talk about all those letters. A. Who is going to tell me who is A letter in ACID?
Atomicity.
Yeah, atomicity. I heard few of you. Atomicity. What does it mean, atomicity? Atomicity means that the transaction, the set of the operations on the database, either go all of them or none. Which means that during, well, let's say that we have 2 writes and 2 reads in the same transaction. When the database is broken during the transaction, none of those reads will be actually written. So this is the atomicity. Either all of them or nothing. C. Yeah, consistency. The funny thing is that the consistency is not guaranteed by the database itself, but by your application, which uses transactions correctly. You can write your software using transactions in that way that your data will be inconsistent during for example, between transactions, because the transactions are misused. It is rather a property of your application if you use the transaction correctly. I letter stands for isolation, so I won't ask you what does it mean. Let's get to isolation after the D letter, and D letter stands for durability. Durability means that once the transaction is committed in SQL databases, it means that your data will not be lost after that commit. So, for example, when you have multiple writes in a single transaction, you committed successfully the transaction, and immediately after the commit, power in your networks, in your database center is down. What happens then? Your data is guaranteed to not be lost. So those are the 4 letters of transaction properties. So coming back to the most important today, the isolation. What actually isolation means? Isolation means that each transaction doesn't know about any other transaction which is running at the same moment. It doesn't care. This means that, well, two concurrent transactions doesn't interfere, do not interfere with each other. There is also a well-known property called serializability, which means, what does it mean? Serializability means that, well, let's say that we are the transaction, like an increment transaction, where we have a key and a value. Let's say that the value is set to 0. It's a number. So we have a transaction which increments the value. So from the point of view of the transaction, there is no other transaction at the same moment in the whole database. This means that the transaction is serializable. So this is kind of a nice property. You probably all of you want to have that property in every transaction. So why should you even care what I will talk about later? You probably will say that, well, I don't have time for that. I don't care. I have a serialization. Well, you can say that, but you are not guaranteed to have always the property. Why? First of all, SQL databases most of the time have serialization disabled. For example, in Postgres, there are lower isolation levels, but we will talk about in the next slide about it. But when we are speaking of the transaction in terms of set of operations in the single database, well, in, for example, NoSQL databases, you have no transactions at all. Probably you will have atomic operation on a write on a single document, but when you have a set of operations, they are not atomic, they are not durable during that, when something happens in the middle. So you should care about those anomalies and how to solve them, because it may happen somehow on any database. Speaking of SQL databases, we have isolation levels. What does it mean that we have isolation levels? It means that I said that we have a serializability property. Unfortunately, this not performing very well on most of databases. So usually you don't want to have full serialization enabled by default. So by default, there are lower, weaker levels of isolation, which means that when you have two transactions running concurrently and writing or reading the same set of data, those two transactions probably will interfere somehow. How? It is defined by those levels. Those levels are defined by SQL standard. There are 4 of them. There is, from the left, the weak isolation level, and to the right, the strongest one. First, we have read uncommitted, which means that the isolation level does not prevent any of read or write anomaly, at least any of them. We have read committed, then repeatable read, and then serializable. We have 4 levels, but when we are speaking of each of them, like for example, read uncommitted means that there is guarantee that at least none of there is no guarantee at all, but it is still be possible that any database can implement it with higher level. you will see in examples later. So, let's go to the first anomaly called dirty reads. Well, first theoretical example. Let's think that let's say that we have a database like key-value store, and we have counters. So we have one counter only called first, and its value is set to 0. And we are running two concurrent transactions in parallel, which do the same thing, which is incrementing the counter. So, well, the left transaction. What does the left transaction do? Well, it starts, then it increments the counter, and after the incrementing the value, it rolls back. It may happen that, well, you lost the connectivity to the database or something like that. It may happen, well, usually when something is broken. So, what happens if the second transaction, which is shown on the right side of the screen, runs at the same time and it has read uncommitted level? Well, it starts, then it reads the value. But let's say, do we have a pointer here? Yeah, we have. So let's say that the left transaction wrote the value, the incremented value. And immediately after the write, the second transaction reads the value. Dirty reads means that though this transaction will actually read the number 1. It means, generally, that dirty read means that the transaction can read uncommitted data. As we can see that the left transaction rolled back to the data, so it should be a 0. So when we do not have this anomaly, this right transaction should read the 0 value, but it doesn't. To show you that it is possible to achieve that, I implemented in Go, as it is a Go meetup. The funny thing that is it was possible to implement it only on MySQL database. It wasn't possible to achieve that result in PostgreSQL. But how did I implement it? Well, I ran 1,000 times 2 parallel transactions. One transaction which does start, update the counter, increment it, and rollbacks. And in parallel, I read the data. I begin the transaction. There is substitution of this thing is about the setting level of the transaction. You can set the transaction level, the isolation level, on each specific transaction by inserting it to the query. Then, when I began the transaction, I read the counter as I showed before, commit the transaction, and then I assert that the read value is set to 0. So it is set to read uncommitted level, and let's say let's see what happens. Unfortunately, this not so fast. It have to run 1,000 times because sometimes it may happen, but sometimes it doesn't. Unfortunately, well, something is not working. Well, yeah, it works. As you can see, as you can see, I assert that read value is set to 0. So it happens that almost 1/4 of those reads were incorrect. So as you can see, it is still possible to achieve that if I specifically set the value to, I specifically set the isolation level. So it is possible to achieve that. Unfortunately, this kind of anomaly, it is achievable only on MySQL database. On Postgres, you can't achieve that. Why? Because this is dirty read, which is prevented by read committed isolation level. This is the second one from from that. This is how we can prevent that anomaly. And the funny thing is that on Postgres database, read uncommitted is implemented by read committed. It's by implementation detail, and they didn't manage to read uncommitted implementation because it wasn't, well, it was inefficient to implement that. So, any questions? Everything is clear for now? Yeah, cool. So, coming next anomaly is dirty writes. So what does it mean that we have dirty writes? Let's assume that also we have the same database, but now we have not one counter but two counters. First one is called first, and the second one is called second. So we have two parallel transactions. What do they do? The left one starts, then updates the transaction, the left one, sets both of those counters to its value, which is number 1 in both of those counters. The second transaction does exactly the same thing, but with different number. So let's go step by step. Let's say that we have a single core machine which runs the database. We have no concurrency implemented on we have no parallelization in the CPU. So the database has to switch the processing. So the left transaction starts, then updates the first counter, and the value is set to 1. Then the database switches the processing from left transaction to right transaction. So it starts, then it updates the first counter with number 2, which is overridden value of the previous write. Then there is another statement which updates the second counter, and then the processing, then it commits, and then the processing comes back to the first transaction, which was held right here, and then there is another update which writes the second counter to value number 1. What happened here? Well, the definition of dirty write is that the transaction can overwrite uncommitted data. Because as you can see, like here, this transaction wrote the data, those transaction overwrote the uncommitted data. So what are the consequences? The consequences are that we have inconsistent state. So how do you prevent that? Well, there is an isolation level called read committed. You can simply set the value to read committed or set it by default. And those two anomalies, you can just forget about them. The funny thing, as I already mentioned, that Postgres doesn't implement read uncommitted isolation level. which does not prevent those two anomalies. I also said that MySQL implements it, but unfortunately it only implements it partially, because if I run the implementation of dirty write test on MySQL, it will, well, there is no possibility to see that. To see how is it implemented, well, I again run the 1000 tests. Each test run in parallel two transactions. Each transaction begins, then updates the counter called first to the same value, and it updates the second value. And as you can see, the first Go routine sets number 1, the another one sets number 2, but then after both of those transactions are finished, then I assert that first and the second counter should be the same. They are the same. And as you can see, I ran the test 1000 times and it happened to be passing always, unfortunately. I could run it for like 1,000,000 times and it will still pass, because it is impossible to have this anomaly on each of the database. Okay, that's it for the isolation level called read committed. This isolation level prevents at least those two anomalies. It is guaranteed by SQL standard. Everything clear? Any questions for that part? No? Okay, cool. So let's go further. We have another anomaly called read skew. So let's come back to the slide of the first anomaly called read dirty read, when the first transaction rolled back the data, the transaction. Now we want to change the thing to that it does not commit, but it does not roll back, but it commits. When we have read committed isolation level, as you can see, there is a difference that even though the first transaction have already written the new value, the second transaction still reads the previous value. But what happens if we add one more read to the same value? Well, let's say that, again, we have the left transaction, which updates the value. We have read committed isolation level still. And then we have the second transaction. It reads the value, which is 0, even though the first transaction wrote the number 1. Then the first transaction commits data, it's right. And then the right transaction reads again the same data. What happens here? There is new value. Even though this is the same transaction, well, we could expect that those subsequent sequential reads of the same data will give us the same result, but it's not. This anomaly is called read skew or non-repeatable read. So, showtime. Read skew. Boom. On read committed, I implemented the test on Postgres here to show that this, well, what happened here? Yeah, this is more complicated situation, but it is much more rare. Yeah, I can guarantee that it will work. Yeah. The 4th time, which means I ran the test 4,000 times, and we had only one fail, one time. So it is really uncommon to see that on production, but it still may happen. How I implemented it? Well, again, I have 1,000 repeats and two transactions. First, it says it is read committed level, and it updates the counter with specific value, like the number 1. Previously, the value was set to 0. And the second transaction will read in the same transaction the same counter twice. And then, when I read the value, I assert those values that are exactly the same. So as you can see, counters are not equal. First was 0 and the second one was set to 1. It means that there was a anomaly. So how we prevent that? There is another isolation level called repeatable read, which means that when we have a single transaction and it reads several times the same data, the same read will be repeatable. This transaction level is the default isolation level on PostgreSQL. As far as I remember, on MySQL, there is not that one, but read committed level. So, any questions to that anomaly? No. Okay, so the last one anomaly I want to tell you about are lost updates. What does it mean? Let's say that we have again the counter called first, like in the same examples before, and we have again two concurrent parallel transactions. So what does the left one do? It starts, then it reads the counter, which should be value 0. Then it updates it increments the value in memory, like in your application, not in the database. And then it writes the updated value. So it sets value number 1. And the second transaction does actually the same thing. So each transaction, well, is an increment of the counter, but not increment in the database, but increment in application. Like you read the value, increment, and write. So we have two increments run in parallel. So we expect that the value should be incremented twice, but it's not, because even though there is a commit and this value is already committed, the second transaction overwrites the same value, which is evidently a lost update, because we lost that update. So what is the difference to isolation levels? But here in Brainy we had an issue that we started with serializable level, because it was much easier to implement it for the first iteration of our product. And it happened that, well, it just times out. We have timeouts set to 60 seconds, and most of the time the database did not fetch the data in that level. But when we checked the repeatable read, everything started to working fine. So I did not have any measurements on that, but we proved that, well, it is faster to the production level. Any other questions? No? Okay, thank you once again. The repository with all those implemented anomalies and with almost all combination with all serial isolation levels is public, and you can well, find it on GitHub. Not sure how I will distribute it, but I think that I will ask Bartek to upload it in Go Meetup.
I will.
Sure. Okay. Thank you once again.